Physics, Chapter 18, 18A section review. Uh, Let me say up front that I assigned this without having my book at home. It was at school. My book's in two halves, and we've essentially finished book A, teacher book, and I needed teacher book B because I assigned 18A section review, and I couldn't really remember what the questions were over. Um, and it turns out that number 8 on this section review requires a spreadsheet from a CD that is also at school. And I'm supposed to give you all the raw data for that spreadsheet, program it into Excel spreadsheet program, and have it do the calculations for you for all the charges on the Millikan oil drop experiment, and then graph it for you and figure the slope of the line and the linear regression and all that stuff. But because we don't have those tools available, and I don't have that data available, I'm going to give you my version of the Millikan oil drop experiment for question 8, and there will actually be a calculation on the worksheet that I'm going to give you, my own question, which will be simpler to deal with than the book question number 8. So let's do the first 7 questions, at least on this section, which aren't too difficult. They're mainly laying down the concepts of the fundamental concepts of electric charge. Number 1, for example, 18A, number 1. It asks, what was the substance that was first reported to have electrical properties, and how is its name preserved and used to this day? Yeah, this is demonstrations actually. This whole little section is really a review of Chem 1. We introduced this in Chem 1. As a matter of fact, trying to justify where did the word electron come from? The word electricity. Well, it comes from a Greek word, electron. In Greek, the word electron in Greek means amber. Uh, the petrified tree resin is probably most famous to you from the movie Jurassic Park, where they found a mosquito trapped in the petrified tree resin, and they pulled the DNA out of a dinosaur from the blood of. Anyway, so amber is petrified tree resin. The interesting thing of it was, as I've shown at school, I don't have any amber at school, but polyvinyl chloride, PVC pipe, rub that with some wool. Um, you can rub paper towel on polyacetate, various plastics, and you can rub a balloon on your hair. We know socks in the dryer, lots of phenomena that demonstrate this mysterious force. But it was most obvious when they went to amber makes nice little jewelry. It's kind of a pretty yellowish color. And they were probably cleaning it with a wool cloth. And however it was first discovered, I really don't know. But it produced a mysterious force. And this was this amber effect, the amber force. Question number 2. Um, of course, we know how its name is preserved. The electron and electricity both use that. Briefly summarize the scientists and the discoveries that lead to the current understanding of electrical charges. Gilbert was probably the first. He was a physician for Queen Elizabeth the First, something like that. There's a little article in the book about him if you're curious about the history. Uh, on page 415. Yes. Um, there were lots of phenomena. Queen Elizabeth the First, yeah. Lots of different phenomena about Gilbert. He was interested in magnetism and And this amber effect, lodestone, was the rock that they found that produced another mysterious force. So he's the one that he promoted experiment. There were a So he kind of got the experimentation part started. That's his contribution. A lot of the theories at the time were based on fluids. They sound a lot like the phlogiston theory in chemistry. If you remember, they thought that when a piece of metal burned or anything burned, it leaked some fluid, which is why a piece of paper or leaves, would weigh less because it leaked some fluid out. But then when they burned metals, they found that they weighed more, and then they had to come up with an idea called negative phlogiston because they were losing negative phlogiston. That's why it gained mass. Oh, anyway, the fluid theories were real popular. Maybe they were easier to understand. Maybe they came from some of the early Greek philosophers that didn't even do experimentation, but they sat around and tried to reason through what was based on observations, what was most reasonable explanations for things. Earth, wind, and fire, and water, the four elements. And phlogiston was an explanation for the gain, the loss of mass when something burned, and also the gain of mass when metals burned. So then it was they tried to apply it to caloric theory to explain heat. When you drilled into something, the reason it got hot is because it was leaking this fluid out. Well, a similar concept was used to explain this mysterious amber effect. The Dufay, I believe this guy's name, was the next one that did some experiment. He came up with two fluids because there were two effects. He thought there was a vitreous fluid, which he called it the electric. That was his name for it was vitreous electric, and what was the other electric name? Oh, let me check it out. Resonance. Yeah, I don't connect with those two words, but for some reason, resin, of course, being the amber was a resin, petrified tree resin. So that's where that word came from, and electric from the Greek word for amber. But he thought there were two different fluids. But then Benjamin Franklin, probably the most famous work with electricity, he changed it to one fluid, but the electric, and some things had excess and lack of. It was either too much or too little. And as you rubbed the wool, if I can remember the story, when you rubbed the wool to the amber, he thought you were rubbing something off of the amber. So he said that the amber was negative because it was losing something. And the wool then was gaining something. Well, he was wrong. It was the wool that was losing something, and it was depositing it on the amber. So now forever, whenever an atom loses a particle on the outside, it's a positive charge. Losing is positive in chemistry because Ben Franklin guessed wrong. So anyway, we know that positive things have actually lost something. Positive. He thought it was gaining, but it turns out it was losing electrons. And negative was gaining. He thought it was losing. But so we don't confuse things continue to confuse things even more, let's explain it like we know that it really is. The gaining of electrons creates this negative. But these were kind of the definitions that they worked with, these three guys, Ben Franklin. And then Thomson actually, and this is where the chemistry also, because the electron was such an important thing, Thomson actually then discovered the cathode rays were actually produced by electrically charging a tube of very low pressure gas, like the old TV picture tubes were cathode rays, old hospital monitors, fluorescent lights, neon signs. There's still a lot of cathode ray tubes out there. But the cathode rays coming from the cathode were electrons. Anyway, number 3 says state the law of charges. Yeah, there were lots of other experimentation in this area, but let's not go through all those details. The law of charges simply, and I tell chemistry students, is the 2 laws explain everything in chemistry, because chemistry is based on this force. 2 laws: opposites attract and likes repel. Yeah, opposites attract, likes repel. Whatever this charge thing is, is it a fluid? Well, it is a force. That's certainly obvious that, and we're trying to offer explanations for this force. So we offer the name charge and the 2 names, negative and positive. There's nothing negative about an electron. There's nothing positive about a proton. But because the names we have to give it some name, and so we borrow names from things that we already understand. Ben Franklin was a businessman. He borrowed language from his business, which was when you removed money from an account, you were subtracting. It's losing something. It's negative, and so you charge accounts. You can create positives by adding to those accounts. Anyway, so the words are just borrowed from other things that we understand. Please don't make any other connections besides that they're just words. We make everything up, right? We make up all the words in science. Sometimes they make sense to somebody who made them up, but they don't necessarily make that same sense to us. Number 4 asks this. Why was the electron assigned the negative charge? Well, it was attracted to the positive plate by Ben Franklin's definition. He just charged by removing particles. He didn't really know how he was charging them, but that's kind of what his experiment was determining. What were these things that created this fluid flow of positive and negatives? And so the plate, essentially, he took a cathode ray tube. I've shown you this in chemistry. There's plenty of diagrams if you want to check out the internet and see what Thomson's experiment was about. Great diagrams, little animations and stuff that really help you understand. But apparently, it was bent. You could see the cathode ray because there was a fluorescent screen behind it, and the particles that were the cathode rays, which now we know are electrons, were exciting that fluorescent material and making it glow. And well, he put a positive plate below that beam, and then noticed that it was bent toward the positive plate. So by definition, this is Ben Franklin definition, BF. Ben Franklin. That's why we called it the negative particle. Numbers, number 6. Wait a minute. Was that 5? No, this is 5. Sorry. Number 5. What category electrical materials is lightning rods? Well, a little bit about lightning rods. Of course, we know that they need to be metal, and they're usually pointy. They're metal to conduct, but they're pointy. Points concentrate charge. Something that's pointed will concentrate charge. When we play around with the Van de Graaff generator in chemistry, and we would if we were had that available to us, we would demonstrate it some more. Now you could see that it's the charge always tends to leave your finger. It tends to leave points on your glasses. If you have any sharp, pointy objects, metal zippers, not because they're metal, but because they're pointy, they tend to concentrate charge. A lightning rod needs to be a pointed thing. One phenomena that that they were fascinated with for many years was the fact that in a storm, even before the storm came up, they could see a glow at the ship's mast because it was the most pointy thing on the ship, and it was the highest in the air. It was farthest from the body of the ship. So as the wind blew across the ship, and the sails especially, the sails and the wind would interact, and it would charge the ship, and the charge would tend to concentrate where it was most pointed, at the ship's mast, and where the charge was essentially exciting air molecules. They didn't know what it was, but now we do. It was making electron transitions, which created a color. It was the color of ionized air, purplish. If you think about it, little sparks that you see, small sparks especially, have a tendency to be a bluish or purplish color. Well, that was called St. Elmo's fire. They thought St. Elmo, not the Sesame Street character, but actually the guardian of sailors. He was there at the ship's mast, protecting the sailors from the storm. But now you can see the same phenomena on a lightning rod on an airplane. They have lightning rods. Now, if you're thinking, well, aren't lightning rods supposed to attract electricity to run it down to the ground? Well, on a house, it's easy to get that misconception because they are pointed and they have a long metal cable down to the ground. But the metal cable is in case the lightning rod does get struck. The purpose of a lightning rod is to get rid of charge. Pointy things tend to get rid of charge because that's where charge concentrates, and the charge pushes each other off into the air. And that way your house doesn't get struck by lightning because it doesn't have a charge. So lightning rods are supposed to get rid of charge. That would make sense then, because airplanes don't have long cables to the ground. They're pointy things on the at the end of the wings to get rid of charge on the airplane, not to attract charge. But we don't want to attract lightning with lightning rods. We want to get rid of charge on the object so that it won't get struck by lightning. So points tend to concentrate charge, and the metal cable is, in case you do get struck by lightning, then it will divert all that energy into the ground instead of catching your house on fire. Number 6. Here, let's start here. The electrics, the test rods that are used in our labs, all of those test rods that we use to transfer charge and to that we rub on something, PVC, glass, um, um, what are the polyacetate? There's several other plastics and glass materials. Well, they're all insulators. The word they used was electrics, but the electrics, they spell that with K, a C first and then K. Electrics. Electric. Remember, the greatest electric that I've shown you in chemistry was the halo that will levitate. Styrofoam is an electric. Rubbing wool on styrofoam creates this distribution of charge. Rubs electrons off of the styrofoam, off of the wool onto the styrofoam rather. Just like a balloon rubs electrons off of your hair. And then you can stick the balloon to the wall. Well, the electrics turns out are insulators. Just a little bit of language for you. And number 7. We're almost there. List the variables that Millikan had to control in his famous oil drop experiment. Well, let's talk about that. I'm going to draw you a very crude diagram, but he had to control the size of the one of the controls. Here, we'll list them. Controls. Size of the box, of the apparatus. Box is just a simple word for apparatus. He also had to control the size of the oil drops. And the viscosity of the oil droplets. For that matter, and the air, because the difference in viscosity of the air and the oil is what determined how much air resistance it had. But the size of the drop determined the weight of the drop, which was gravitational pull on the drop. But he also had to control the voltage that he applied because he was trying to charge these oil droplets. The voltage on the plates. And there's lots of other things too, but those are just a few. Well, just a crude diagram. We have to spray oil into the box. Little tiny drops of oil, like an atomizer, spray bottle, little mist, if you want to call it. So you could call it an oil mist if you want to. He would, the floor of that box had a hole in it, so you could, one of the drops would come through the little hole in the bottom. He would be able to see that with a microscope. So he's looking at the oil drop with the microscope, and then he has to have this connected to high voltage. We'll just call it V, the voltage. This was a negative plate down here, positive plate up here, negative and positive plates. Oil droplet goes through, but how are we going to affect the fall of the oil drop unless we have charge on the oil droplet? That's where the X-rays came from. You had to, here, an X-ray source, actually to ionize the air molecules, X-rays coming out there. knocking electrons off of air molecules. The air molecules losing the electrons would get stuck on the oil droplets. So the oil droplets coming through here with electrons that have been robbed from the air molecules. Of course, there's a downward force on the air droplet, right? The downward force. We know that's gravity. We call it the weight of the oil droplet. There is an upward force on the oil droplet, which is the viscosity of the air, and it will reach terminal velocity. Here's some of the tough equations that was introduced, but let's simplify things by saying that the weight of the oil droplet minus the buoyant force of the air would actually be the downward force. But we're going to ignore the buoyant force of the air. It's a pretty tiny oil droplet. Okay. There is an upward force on the oil droplet, though, created by the electric field, the voltage. So we have this upward force. Just to designate it from weight, we'll call it electrical. And the electrical force turns out to be not M, but Q. The charge is kind of like mass with gravity. And this is honestly the whole oil drop experiment, besides the fact that chemistry depends on this understanding of how much charge the electron does have, because it's also the charge on the proton. It is a fundamental particle for our universe. God has created things, and if the charge on the oil droplet was anything different than it is, the charge on the electron was any different than it is, we wouldn't be here to talk about it. There are hundreds of these little constants that have to be exactly what they are. The charge on the electron is the smallest unit of charge in the universe, the smallest amount of charge. It is we'd call it the fundamental charge of the electron. Well, instead of G for gravity field, we have another quantity called E, which is electric field. So we have an analogy between this is actually in chapter 19, I think, that they talk about electric fields. Well, electric fields are kind of like gravity fields. As a matter of fact, they could be written that way. The force divided by the mass is gravitational field. The force divided by the charge is the electric field. That's just a way of describing this area that exerts force on charges. They call it electric field. It exerts force on charge. There's an electric field right here. It's exerting force on the charged oil droplet. How did the oil droplet get charged? Well, it picked up electrons off of air molecules because of the X-rays, knocking them off. The thing of it is, we don't know how many electrons are on the oil droplet. That was the tricky part, which is why the book wanted you to put in all of these numbers. They want to take into account the buoyant force on the oil droplet also, and the equation. Yeah, you ought to check that out. It's really pretty amazing. The complication when you take the concept, which is basically pretty simple, these two forces are balanced. He can do that by varying the voltage so that he can get that oil droplet to stop. In which case, the two forces are balanced. But if you take into account the buoyant force and the viscosity difference between the oil droplet and the air, and you want to get a little more precise of a value, if you're talking about the tiniest, this is the tiniest mass, is the electron, and the tiniest amount of charge, you can imagine, a little more consideration has to be made for some of the details. In which case, you come up with an equation. If you don't have your book, the equation they were using was the total charge on the oil droplet, not the electron, but the total charge on the oil droplet, 1.59122. Very precise. Again, by graphing, if you do this lots and lots of times, you'll get very precise numbers. Times 10 to the negative 8. Um, 1 over the voltage times the square root of the falling terminal velocity. The first V here is voltage. This velocity, we'll call it VT for terminal velocity. That would be, of course, how fast it was falling when the weight is equal to the air resistance. You know what terminal velocity is. Cubed times the, divided by the difference in density of air and oil. So, well, there was supposed to be an equation on this CD with all of this data for this whole table, if you have seen this table in your book, and essentially plotting all of the the oil drop charges. So essentially what they do is they plot the oil drop charges and versus the integers of the trials, which at first you would think, well, why is that? Well, because if you do enough of these, what's going to be the difference between the smallest amount of charge on an oil droplet and the biggest amount of charge on an oil droplet? It will always be some integer times the charge on the oil droplet. That's the electron, sorry. Here, let me write it out. Qn, the total charge on the oil droplet, has got to be the charge on just one electron times some number, n, the integer. So if you graphed them, you would get the slope of the line would actually, the change every time an electron is added should be the slope of the line would then give you the charge on the electron. That's all very messy. Even when I try to simplify it, it's still pretty messy. But don't lose sight of the forest for the trees. The beauty of it is that God has created the world in a way that the charge on this electron, this smallest amount of charge, has to be exactly what it is for the universe to exist, for elements to form, for atoms, for life, for us. He truly loves us. And number 8 essentially is hidden in all this, so don't worry about doing the instructions that number 8 tells you to do. Dear God, thank you for making the world like you have, for giving us the electron and the charge that is exactly what it needs to be. In Jesus' name we pray. Amen. I think, did I forget something? No.